All right. Good morning, good afternoon, good evening, and good night to all of you. So today is going to talk about the recording is about chapter number 12, which is actually the final chapter for this course EBE 2174 econometrics. It's a last chapter, but it's not the end of econometrics actually, because pretty much we have discussed from the beginning of the semester that we talk about the subject. When it talks about the estimation, the methodology that is suitable for the estimation. And right now we are pretty much in the end. Talks about this chapter number 12. And pretty much that's what we're going to have here. Pretty much this whole idea of this, again, this chapter number 12 talks about this particular chapter. The focus will be on the autoregressive distributed lag model and the Granger causality. Though there are few terms that is important, which actually you'll be they'll be moved forward towards the other subject. So this is the starting point of the other subject. Let me stop my video so that so they do not disturb any one of you here. All right. So again, this is chapter number 12. So let's move forward to the next slide. So based on that, the introduction is that we have to understand, based on the certain idea behind base. Let me stop this sharing again. Okay, so sorry for that. Resume back. Okay, let me. Okay, yeah, this is how it's supposed to be. Go to the wrong place. All right. In the beginning, if you have what we call actually as a lagged dependent variable, we have done this part a little bit on in autocorrelation, but now we also include the X lagged inside there. So here, rather than having the this part, which is we done in a autocorrelation chapter, right now we have something like this. So to introduce, again, go back here, we have we have time t, we have t plus 1, and we have t minus 1. In a much more clearer version, actually, if you are having this, you have a t, and then you have a t minus 1 and t plus 1 in this regression function, right? This t refers to, for example, today. T minus 1 will be yesterday, if the data that we have is actually looking into daily data, and t plus 1 will be tomorrow. All right, so let me clear this thing up and put this thing back. So moving forward in that sense, so we have the regression not only just having the current, but also the lagged past value. Why that is important? In other sense that we expand the model in time series model, especially to regards the idea of whatever happens yesterday would determine today, and whatever happens today will determine tomorrow. If we talk about, again, daily data, or whatever happens last year or whatever happens this year will impact next year, and so on. So that's what we call about, that's the name of distributed lag model, or in short, it's called DL. The AR model, we have done that in the chapter number 9. We have AR1, AR2. If you combine both, we call it ARDL. If you have both, means that you have XT minus 1, XT minus 2, for example, here, and you have YT minus 1 here. This type of model, we call it ARDL model. It's not a new terms. Perhaps some of you have come across the word while you're searching for the literature review and searching for the suitable literature, and for your searching for your FYP topic, you come across with some literature talks about ARDL model. So that's the ARDL basic here. So now we are doing some basic understanding of the model. So we have distributed lag model, we have AR model, we combine it, it becomes ARDL. All right. So these are a few examples of how the development of the AR model this DL model and AR model into how we develop into the AR understanding, AR model understanding. Here we have, for example, the Koyek transformation distributed lag model. Started off 1954, that's more than 50 years ago. We have this infinite lag model, which have this type of modeling structure. This is a DL types of model. And this, assuming that all the betas are the same sign, the Koyek assume that they decline geometrically following these terms. And the lambda itself, the lambda here, right? The lambda here actually measures the speed of adjustment. So here, this field model actually talks about the extension of the model that we discover, that all of you will discover in your next subject called modeling in economics, which talks about speed of adjustment. So there's a few similarities here. Talks about the modeling structure. All right, it implies that the speed of adjustment is imply how fast does the adjustment go. So in this sense, is the decay or the rate of decay in that sense. Right? In that sense, if you interpret in such a way, it says a beta when it goes one back to the distant past effect of the lagged y becoming progressively smaller and smaller. Means that to acknowledge this type of model, expand the model just for the current view. We expand some past information also important, but that past view impact would be decaying, or they talk about the adjustment process. How fast is the adjustment process? This is an important, not just for econometric modeling, but also for economic understanding. All right. So here we assume that when you calculate in that sense, when you transform it into the model, it will be coming where you have this lambda inside there. Right? Transform it, become lambda, and then after the transformation, in the end, the rearrangement in the end, like equation number 7 here, we call it Koyek transformation, where we have this lambda here measures the speed of adjustment, right? Speed of adjustment from which, how fast does this variable t-1 will be able to know and explain the current t or the current y in this sense. So we know that the understanding right now is that previous information is important for the current information, means that historical does matter. But the question now is that the question that expanded by this model, even in 1954 model, is that how fast is actually the adjustment towards the current situation? How fast is the adjustment? How rapid is the adjustment? Or how slow is actually the adjustment? So this is one example of Koyek transformation. All right. Yes. So from distributed lag model ended up with autoregressive model because yt-1 appeared as one of the explanatory variable. This one actually, this appearance of yt-1 will create some statistical problem, especially in what we understand. And certainly the presence of lagged dependent variable actually violates the assumption of the Durbin-Watson. So you should use the Durbin-H or the Durbin or the Bruce-Grothe to estimate if, let's say, you have this this type of variable inside your regression. And you remember back the chapter number 9 where I put up the quiz for you, right? Online quiz for you to answer, to try to calculate the Durbin-H without this term. It's not possible. It's not possible, right? To repeat it back again. The second model that we look at before we entering the next part will be on the adaptive expectation model, right? Adaptive expectation model. Here, in this particular regards, right? In this particular regards, this type of model here, comparatively to the Koyek model, this one actually also, the original model looks something like this, adaptive expectation. This is also from somewhere about 50 years back. And they have this sign here, the theta sign here, which represent coefficient of expectation. Right? which is almost similar of the speed of adjustment, almost similar of what in correct model. But the difference is that again, the idea is that if you read here through hypothesis 2, it's not an adaptive expectation, progressive expectation, or error learning hypothesis. It means that the learning agent will adapt the expectation in the light of the past experience, and that particular, they will learn from the mistake. So this is rather interesting thing. We learn from our mistake, we learn from the expectation what we have from the last period of time, and we learn for the betterment for the future. And this is the measurement. So now, to include that inside the model is rather interesting. So here, this particular chapter is actually to introduce something that is not available in all the other chapters before this, right? Introduce something new in this particular regards. Okay, so this is that will be something I mean pretty much interesting in that sense for this particular example. All right, this particular example. Okay, so here here again the idea behind when you derive this thing all to means that you have an expectation, the calculation of coefficient of expectation. So the value will be from 0 to 1 normally, right? So either is the minimum is 0, the maximum is 1, means that the expectation might be 1, means that 100% expectation, or 0 point something with this regards, right? So based on this transformation, you get the types of modeling structure like that, like this one, that equation 4 and equation 5. This is just the transformation of how it will transform to include the t-1 inside there, and that t-1 contain a very important information of what happens in the past and put it inside the current regression. That's what it's supposed to be. And both model, adaptive expectation and correct model, is both autoregressive model, and both have the same error term, although interpretation of coefficient might be different, right? Certainly this has been extended by the people after that of rational expectation people. And the third model here, it talks about partial adjustment. Similar idea behind is that we include the past information here, represented by the delta here, the partial adjustment where this delta represent the adjustment, which is the value from 0 to 1 of how of the changes happening yt minus 1 means that the previous information will be important for what is happening right now. Right? We learn from the mistake. We learn from all the mistake, like what is happening right now with this ongoing pandemic. The world is actually learning from the previous pandemic, so that we can improve much more better and recover much more faster. So there's a lot of learning curve experience from the previous pandemic, and also for the current one, because as of we are in the 2021 right now, and what we have learned from the previous year and from the previous year when it started off and so on. So things change for the betterment, and this adjustment, if you can measure it and put as one variable, will be an important information for the future. All right. Same thing goes to when you talk about important policy making. They'll be very important for policy making, especially in economics and finance and some other things. Some other information, important information. What happened in the past will be an important information for the future, and what happened right now will be important for tomorrow. The best example normally I will give will be like the weather forecast, right? Yesterday weather will be important for today, and today weather will be important for tomorrow for forecast. Even said so, the forecast for the weather actually been done every hour perhaps, or every few hours, and the weather change and the forecast should change too significantly. So same thing here. So means that the weather forecast actually use the previous information to forecast the weather. But on the same dot, when it happens at the dot, then the weather might change significantly and the forecast will change significantly too. Right? Same thing here in that analogy used in that sense, right? So substituting transformating this partial adjustment model, you get the final model is all about the autoregressive modeling, right? So this is the summary. All have the common form of an AR model. This is the final model. But what we have here, we have the adjustment, the Koyak so-called transformation in that sense, that measures the speed of adjustment, that measures the coefficient of adjustment and so on, right? Okay, the next one is that how could we put this model inside what we have, what we understand inside the classical linear regression, right? How it can be in that sense, so that it will not disturb the blue properties and so on. All right. So we would be able to expand the model to include the lack of dependent variable, which I already shown you actually in the previous chapter number 9. One of the solutions is actually using the lack dependent variable for the problem of autocorrelation because it involves time. Autocorrelation involves time, t. Heteroskedasticity does not involve time. So that's why the solution is like weighted least square and so on. Multicollinearity also do not necessarily involve time because it can happen in both scenario. Right? That's the main three things that I talk about. The Ramsey reset, Jabera refers to the different issues. Kusum test refers to stability. Right, now we move forward to the so-called the other section, which is called Granger causality. The simple words of Granger causality comes about from the word causality, cause, from the word cause, and it's been developed by a person called Cliff Granger. Right, he's no longer with us, right? But it's very, very, very important article. 1969. It's more than yeah, it's been a while, more than 40 years right now. So the intuition behind is simple. Let me give you a very simple example of intuition behind of Granger causality. How we explain Granger causality in much more simple terms. Imagine, you have the husband and wife, right? Oh, this is a bit terrible, right? Let me put this thing up. Right, husband and wife represented like this. Let me create this thing. Let me draw it again in a much more better way. Oh, oops, not yet. Finish, yeah. Let me draw. Let me some highlight there. Right, you have husband and wife. Right. So how to explain this to is either way in a simple analogy is that husband can cause wife, means that husband determine what wife decision is. For example, means that husband control wife. So Granger causality come from husband to wife. That's one. The second possibility is that a wife control husband. So means that the Granger causality, the causality goes from husband and from wife to husband, means that wife determine all. All right, that's the second one. Yeah, here. The third possibility is that husband and wife cause each other, means that they do mutual decision. Husband and wife cause each other. That's the third one. And the fourth possibility is that no direction of causality. No direction of causality means that the husband and the wife, no relationship, despite that they are husband and wife. In this sense, normally I would say that the husband has some scandal outside, then the wife has some scandal outside. Maybe a causality outside this relationship, this bubble relationship. And then the relationship outside, that's a different relationship. So the husband cause, or the husband have some relationship outside this legal relationship, and that is illegal. That is simple analogy of Granger causality, which is this 4. If we have 2 variables, you have 4 possibilities. If you have 3 variables, you have more possibilities, and so on and so on. You can easily execute that inside for your project. It's necessary for your project. So basically, this is what happened. Right? The intuition, the simple intuition, and we use the calculation is using the simple F test. But in eViews, you just click it, you come out the result and interpret. The null hypothesis is no causality. Null, hash null, no cause. Right? Hash alternative you reject means that you have a causality between the variables. All right? So particularly, that's what really happens here. For example, like this. And the extension certainly would be available inside your the next subject on the VECM, variance decomposition, impulse response, and so on. That's the extension. All right? That's for now. That's for now. It's not the end yet. We'll show you the eViews. I'll show you the eViews how to do Granger causality and how actually to introduce lack of dependent variable inside your model of the regression. All right, I'll introduce you to that and this part of it. Right. Let me stop this sharing first. I'll go back to my screen sharing so that you can have this thing back. Right, discard. Let me go through this screen sharing here. Recording. Go to eViews. Straight away go to eViews. Again, straight away go to the data that we have, the manufacturing total export and GDP. Use this example. Now we want to estimate Granger causality. We want to estimate Granger causality. Okay, how we do that? Very simple. Let's choose GDP, export, and manufacturing. Here we have 3 variables. Just now the example in the notes, you only have 2 variables. Open as a group. Open as a group. Right? Choose variables. Open as a group. Right? Open as a group. Okay? Yeah, in that sense. We do this. View. Straight away here, you have go view. There's a word there, Granger. There's a word Granger here. There's a word Granger here, Granger causality. Right? So what you can do here it suggests by eViews, it says that like to include 2. You can present the Granger causality from leg 1 to 5. I'll show you how to do that. Simple. So Granger causality, I'll change this to 1 first. Leg 1 to 5 means that, what's the meaning of leg 1 to 5 means that the t minus 1, t minus 2, t minus 3, t minus 4, and t minus 5. So click OK. This is the result of Granger causality. F statistic probability is here. So leg 1 to leg 5. So we introduce from results from leg 1 to 5. Right? To this is rather important to check consistency. Important to check consistency. So this is leg 1. So this is the result. So you can always copy and paste this result to Microsoft Word and so on. What reject, what do not reject? Let's say you choose 5%. 5% significance. So here, based on leg 1, I will interpret that GDP does not Granger cost export is rejected. Right? GDP cost export. In this case, GDP also cost manufacturing. How we see this, how I see this here. Simple. Use this simple. This is not. Manufacturing does not cause GDP. Do not reject. So you do not have that kind of relationship. And the last one here, export cost. Export to menu. Not rejected at 5%, but at 10%. So 5% not rejected, so no relationship. No causality relationship. So we have these two causality relationship. Only these two, not this one. Right? You see here, 0.09 is larger than 0.05. So that is leg 1. Let's say leg 2. Right? This is leg 1 result. This one, I put it down. This is for leg 1. LIG 1. Leg 2. If let's say you have leg 2, right? Leg 2. Let me estimate leg 2. Leg 2 right now, let me change here. Go back here, you change to 2. Then this is the result. The result seems to be in leg 2. It is the same as leg 1. You see here, it's still rejected. This one still rejected. This one all not rejected. All right. Leg 3. Let me do this for all of you. Leg 3. See what happened. Still similar result. Not only similar, the same result. Leg 4. Let me see leg 4. Let us see leg 4, right? Leg 4 here, now you have a little bit different result here. You have 1, 2, still the same, but now you have additional. You have additional here, manufacturing does not Granger cost GDP. It's also rejected at 5% because it's lower than 0.05. Additional causality exists where menu cost GDP. Right? Leg 5. Leg 5. This is leg 5. What does that mean by this one? 1E negative 0.5, 1E 0.5. It means that it's a very, 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 very small number. E minus on D negative 0.5 means that it's very small number. Means that it's 0.0003, 0.0001. Very small number. Same results as leg 1, 2, 3. So it's quite consistent. It's only leg 4 we have a little bit different result. Why I do leg 1 to 5? This means that I assume that leg 1 could be a very short period of time. Leg 2 can be leg 2 and 3 could be a medium period of time, and leg 4 and 5 could be a little bit longer period of time. Means that in this case, in my case here, leg 5 means that 5 years before. Leg 4 means that 4 years before this. Leg 3 means 3 years, and leg 2 means 2 years, and leg 1 means last year, for example. But this is not last year because our data is a little bit outdated. So it means that that particular year, what happened 5 years ago still would impact as of current. That's the meaning here. That's the meaning of Granger causality. All right. So that's the Granger causality that I want to introduce to you, that it should be included that also in your project as part of the estimation. Okay. That's what is it, right? So for 3 variables. For 3 variables, you come up with 6 possibility here. 6 possibility. Just now 2 variables is only 4 possibility. If you have 4 variables, you have more possibility, and so on and so on. All right. Things change here. You see the observation. If I put leg 1 is only is 34. If I put leg 5 just now, observation is 30 because it's reduced. It reduced the sample once you increase the leg length. So again, the idea behind always is that the bigger the sample, the better is it. But sometimes I produce a little bit different result. All right. That's all for now. That's all. That is all for now for this particular chapter, Granger causality. Hope everyone could understand, or if not, that you can refer back again to this video a few times so that you understand. Take care, all of you. Stay safe. I'll see you in the online class for this particular chapter. Ciao. Adios.